Hello friends, now we will start with the next chapter of EDC and analog electronics, that is multi-stage amplifiers. Remember, the multi-stage amplifiers are used when the voltage gain of a single stage or current gain of a single stage is not sufficient. Suppose I want to achieve a voltage gain of 10 raised to power 4. In that case, and if single stage is able to give me the maximum voltage gain of 100, in that case I will be connecting two amplifiers in cascade, where the output of one stage is fed to the input of next stage. So in multi-stage amplifiers, what do? We connect output of one stage to the input of next stage and so on. In multi-stage amplifiers, there are important points to be noted. There are different coupling devices between input of the next stage and output of the previous stage. We classify the multi-stage amplifiers on the basis of those coupling devices used. For example, we have RC coupled multi-stage amplifier. There are basically 3 to 4 types of multi-stage amplifiers, but most commonly classified are 3. RC coupled multi-stage amplifier, in which we make use of RC resistance and capacitor for coupling of output of the previous stage with the input of the next stage. We make use of transformer for coupling. We make use of inductors for coupling, and last one is direct coupled. So in fact, we can say 4 types of coupling multi-stage coupled multi-stage amplifiers: RC coupled, transformer coupled, induction coupled, and direct coupled. But in most of the cases, in most of the exams, we have questions on 3: transformer coupled, RC coupled, and direct coupled. But most commonly used is RC coupled because of certain advantages. We will see the circuits, different circuits of these amplifiers in the next few topics, where we will be discussing each type of multi-stage amplifier one by one, depending upon the type of coupling used. But before that, let me clarify. Ultimately, we have 3 configurations in amplifier applications. What the configurations are: common emitter configuration, common base configuration, and common collector configuration. These are 3 types of configurations which are used in BJT amplifiers. In common emitter configuration, the voltage gain is moderate, more than unity. Current gain is moderate, or we can say both voltage gain and current gain are more than unity and higher. When you compare the common collector configuration with common emitter, what is high? In case of common collector configuration, voltage gain is less than unity and current gain is high. In common collector configuration, which is also known as emitter follower configuration, current gain is high, voltage gain is low. So suppose we have multiple stages in the amplifier like this: first stage, second stage, third stage, and so on, like this. Fine. If I make this is intermediate stage, this is input stage, this is output stage. So in case of common collector configuration, the voltage gain is less than unity but of order of unity, maybe 0.98 suppose, right? So in case of common collector configuration, if I make use of this amplifier here, what will happen? Remember, in case of multi-stage amplifiers, the voltage gain of these stages will be multiplied to get overall voltage gain. Similarly, current gain of these 3 stages will be multiplied to get overall current gain. So when you multiply, if suppose this is common collector, this is common collector, this is common collector, and there are suppose 4 stages. This is fourth one, right? This is also common collector. So what will happen? In this case, voltage gain of the common collector is low. So multiply to get overall voltage gain. What I do? I multiply this voltage gain 4 times. And when you multiply a quantity which is less than unity, the overall gain will go on reducing. For example, if you have voltage gain of one stage 0.9, voltage gain of two stages will be 0.9 into 0.9, and that is how much? 0.81. So that means the overall voltage gain has reduced in comparison to the single stage. So what happens? If you make use of common collector configuration in intermediate stages, the overall voltage gain goes on reducing. Of course, current gain is multiplication of two stages, so current gain will increase, but voltage gain will decrease. So because of that characteristic, we don't use common collector configuration in intermediate stages. We don't make use of common collector configuration in intermediate stages of a multi-stage amplifier. You should remember this question, this point, because there can be question, objective type question in engineering services exam. First of all, you should know the importance of this chapter. This chapter is important for engineering services prelims. This is very important. You have a lot of questions from this topic in engineering services prelims exam. It is not important for mains exam. 2. There are many questions in gate exam from this chapter, especially in electronics engineering. Fine. So for electronics engineers, it is important for gate as well as engineering services. So there can be question on this. Why common collector is not used as intermediate stage? Because there may be 4 different reasons, out of which one may be correct. Because its voltage gain is less than unity, and overall gain goes on, overall voltage gain will reduce because of the multiplication of the gains. Similarly, if I make use of common base configuration here instead of common collector configuration, we know in case of common base configuration, current gain is less than unity. The current gain of common base configuration is less than unity, but of order of unity, maybe 0.97 or 0.98 or so on. But that is definitely less than 1, but about unity, near the unity. So same situation will arise here. If common base is used here or maybe everywhere, in that case current gain will reduce like this. So that means common base configuration and common collector configuration is not preferred in intermediate stages, means these stages, in case of multi-stage amplifier. So which is suitable? Common emitter configuration is the most suitable configuration for intermediate stages. But common collector and common base configurations can be used at input and output stage because of their typical characteristics. For example, common collector configuration has excellent quality or excellent characteristic of impedance matching. It matches the high impedance source to the low impedance load. Input impedance of the common collector configuration is very high and output impedance of common collector configuration is low. So it can be used for matching of high impedance source to low impedance load, like that. So at input and output stages, we can make use of all 3 configuration: common collector, common base and common emitter. But at intermediate stages, we always prefer only common emitter configuration. Do remember it. There can be objective type question on this. I'm not writing this thing on board, but I hope you understood the concept. Fine. Now, once you understand this, I hope you understood the concept why we make use of common emitter configuration in intermediate stages of a multi-stage amplifier. Now, let us talk about the overall voltage gain, current gain and power gain of multi-stage amplifier. I have already told This is a multi-stage amplifier where the output of one stage is fed to the input of next stage like this. This is stage 1 amplifier, this is stage 2, this is stage 3, and you can connect n number of stages like this. So input of this is output, this is output of first stage, but input of next stage, and so on. In general, there are two possibilities. There can be no interaction between input and output stage. What is the meaning of no interaction? Meaning of no interaction is the output of the first stage is same whether it is connected to the next stage or not connected to the next stage. When output of one stage is not affected by the input impedance of the next stage. I repeat, when output voltage of the previous stage is not affected by the input impedance of the next stage, then we call non-interactive type of multi-stage amplifier or non-interaction among the stages. That is not a fact. We will see it one by one. So I'll be talking about two cases now. Case 1, non-interactive stages. So when you have non-interactive stages, what is the meaning? When output of one stage is not affected by the input impedance of the next stage, or output of this stage is not affected by input of impedance of next stage, those type of stages are called non-interactive, that is non-interactive stages. In that case, overall voltage gain of these multi-stages is equal to the product, the multiplication of the voltage gain of individual stages like this. Simple multiplication. If these are 3 stages I have shown, you may be talking about n number of stages. So this is nth stage, this is stage n. In that case, the overall gain is like this. Overall voltage gain is like this. Fine. Now, gain can be taken in decibels. I hope you remember, but I'm just repeating. Suppose you have gain AV. You have gain AV. That is simple gain. You can represent this in decibels also. Decibels are basically this decibel range gives you the decibel covers the wider range. In fact, wider range of values of the gain. So in decibels, this is written like this: 2 log base 10 AB. Fine. So this was a simple gain. If you take it in decibels, so what do we do? You simply take 20 log base 10 AB equal to 20 log base 10 AB. Take log on both sides, multiply by 20 on both sides. So this will be AB1, AB2, and so on, ABN. And you know log of multiplication. So what that will be what? This is AB in decibels is equal to, and that will be simply log of what? When you take log of two quantities, log of x, y, if you remember, x, y, z is what? Log of x plus log of z, y plus log of z. I hope you know the property of logarithmic. So if you know the property of log, in that case, what do we do? Log of 20 log AV1 plus 20 log AV2 plus 20 log AV3 and so on plus 20 log AN. And this is what? Log, that is voltage gain in decibels will be equal to AV1 in decibels plus AV2 in decibels and so on plus AVN in decibels. So it means when you talk about simple voltage gain, so overall voltage gain is the product of the voltage gain of individual stages. But if you take log in decibels, then if you take your voltage gain in decibels, then overall voltage gain is decibels is the sum of voltage gain of individual stages in decibels. So here it is multiplication, but here it is sum. You should remember this. You should remember this. These are important questions for exam. There can be objective type questions in exam based on this formula. I hope concept and funda is clear. Similarly, if you talk about current gain of these these are non-interactive stages. So for non-interactive stages, what do? It is simply current gain. So replace this symbol V, that subscript V, by I. That's it. Otherwise everything is same. The overall current gain of all the stages is product of current gain of individual stage. So it is simply multiplication. Everything otherwise goes similar to what we have discussed in case of voltage gain. So here simply replace this subscript of V by I. That's it. Otherwise mathematics is exactly same what we discussed for voltage gain. That's it. This is the voltage gain, current gain of different stages. That's it. So in logarithmic, in log you can say, or in decibel you can say. In decibels, overall current gain is algebraic sum of current gain of individual stages in decibels. So here it is multiplication, here it is sum. Please remember this point. Fine. Now this is current gain. Let us talk about power gain. Power gain is also exactly similar to what we talked. So it is overall power gain of first stage, power gain of second stage, power gain of third stage, power gain of nth stage. So overall power gain is again multiplication of power gain of individual stages. And if you remember the previous topic, I am just repeating, the power gain is simply product of voltage gain and current gain. Please remember that. Power gain is product of voltage gain and current gain. And similar to the voltage and current gains, the power gain in decibels is simply algebraic sum of power gain of individual stages. But there is important point. Important point is what? If you take power gain in decibels, in case of voltage gain it was 20, but in this case when you take power gain in decibels, it is not 20, rather it is 10. So outside factor, instead of 20 for power, this is 10. Overall power gain in decibels is what? 10 into log with base 10 into AP. This is the difference in power, voltage and current gain. In case of voltage and current, it is 20 outside in dB, but in case of power it is 10 outside in dB. Otherwise, as far as expressions are concerned, expressions are similar for voltage, current and power. Fine. So this is voltage and current gain of non-interactive stages. So I can have n number of non-interactive stages where overall gain will be product of gains due to individual stages. Fine. This was case 1. Let us talk about case 2, that is interactive stages. What is the meaning of interactive stages? If voltage at output of the first stage is affected by input impedance of the next stage, voltage at output of this stage is affected by input impedance of the next stage, then the stages of the amplifier are interactive. You cannot take voltage at output in isolation. So in that case, overall voltage gain has to be obtained by adopting certain different technique. Let us see how that technique will be adopted here. So I will be taking just for mathematical simplification, I will be taking 2 stages instead of taking multiple stages, because otherwise mathematical expression will become little complicated. Fine. So let us see that procedure. So I'll be taking 2-stage amplifier here. This is the first stage. This is the second stage. That is interactive stages. Fine. Now, general block diagram of a voltage amplifier can be drawn like this. We know every amplifier has input resistance, every amplifier has output resistance, like this. This is Ri1, R01, Ri2, and on this side it is R02. Resistance seen from this side is input resistance of the first stage. Resistance from this in this side, that is output resistance of the first stage. So this is first stage. I'll say stage 1. This is stage 1. This is stage 2. Fine. So in stage 1, I have a resistance which is nothing but input resistance of the stage 1, Ri1. Then I have, this is voltage, which is of course overall input voltage V in. This is overall output voltage V naught. Of course, the output of the second stage is overall output voltage. Input of the first stage is overall input voltage. Now, if you remember, in case of amplifiers, we have one source here. That can be voltage dependent current source, that can be voltage dependent voltage source, that can be current dependent voltage source, and so on. So in this case, I will be taking this as voltage dependent voltage source. How? Because this is voltage amplifier I am talking about. So voltage gain of this stage multiplied by input voltage. And this AV01 is nothing but open circuited voltage gain of stage 1. Fine. And if it is a voltage source, so we connect our resistance here on output side of stage 1. This is general block diagram of a voltage amplifier. I repeat, general block diagram of a voltage amplifier, where this dependent source is voltage dependent voltage source. This is input resistance, and resistance on output side is connected in series with the voltage source. Fine. So similarly here, I will be connecting a resistance at input of the amplifier, and that is input resistance of the second stage. Exactly like this, I have resistance here, that is output resistance of stage 2. I have voltage dependent voltage source here, that is nothing but AV02 into what? That is V in 2. So here at input of this is what? V in 2. But at output of first stage is what? V01, and both are definitely same. So output of this stage is input of the next stage. So this is the general block diagram. Now, why I said interactive? Please see it. If I open these terminals, you disconnect it. In that case, what will be current in this resistance? 0, because there is no path for the current. And if there is no path for the current, will be the output voltage, same as this voltage. So V01 will be equal to AV01 into V input. That will be the output voltage. So AV01 is equal to what? V01 by V input. AV0, that is AV01. That means this AV01 is the voltage gain of the first stage under open circuited condition, right? But if I connect it here, In that case, V01 will be equal to what? This voltage source, voltage dependent voltage source will supply current here. That current will pass like this. So voltage across this resistance will be the output voltage. So that will be Ri2 divided by sum of these two resistances. This is simple voltage divider rule. If you don't know, please remember, if there is a voltage source here and two resistances are connected in series, so voltage across this resistance is this resistance divided by sum of 2 multiplied by this voltage is the voltage across this resistance, that is nothing but output voltage. So this is AV01 multiplied by V input. And if you compare this and if you compare this, what has happened? That voltage which was at output is not same, but that has reduced. Voltage at this stage has reduced in comparison to this. The output voltage has reduced here, or input voltage has reduced here when you connect and disconnect. Under open circuited it was this, under connection when both stages are connected, so the output voltage is this. So that means there is interaction between these two stages. So that is why we call as interactive stages. Fine. In previous case we consider same. If you talk about non-interactive stages, so voltage gain, overall voltage gain will be taken like this, AV1 multiplied by AV2. Simple product of these two gains we take. But in case of interactive stages we don't take. Fine. So you have to remember like this. So here when these two stages are interactive stages, output of the first stage will be reduced because of the interaction of output of this stage and input of next stage. Fine. So let us go one by one. I hope you understood the concept of interaction among the stages. Input impedance of the next stage affects the overall output voltage of the previous stage. That's what I'm trying to say. Now, what is the output of the first stage? Let us see that. The output of the first stage V01 is equal to what? I have just shown you that. That is Ri2 divided by Ri2 plus R01 multiplied by AV01 into V input. Fine. What is the output of the next stage? V0 will be equal to, here I am taking open circuited, so there is no voltage drop across this. So whatever is this voltage, that will be output voltage. So AV02 multiplied by V in 1. Sorry, V in 2, that is input voltage of the second stage. And input voltage of second stage is what? Output voltage of first stage. So I can simply replace, or I can simply write, that is AV02 into V output of the first stage, right? V output of the first stage. And you know what is V output of the first stage? So that is nothing but AV02 multiplied by Ri2 divided by Ri2 plus R01 into AV01 into V in. So overall voltage gain will be what? Overall voltage gain will be V0 by V in. Output voltage of the combination divided by input voltage of the combination will be the overall voltage gain, and that is equal to what? You can please see that AV01 into AV02 multiplied by Ri2 divided by Ri2 plus R01. This is overall voltage gain. This is important. For gate, there was question, there was a numerical in gate based on this. This is important for engineering services. There was numerical in engineering services on this. There can be multiple stages, but that procedure will go on like this. Fine. So what has happened? If you take non-interaction, no interaction among the stages, the product of the gains will be the overall gain. But if you take like this, interaction among the stages, gain has reduced because Ri2 will be divided by sum of 2, so that will be definitely less than 1, so overall voltage gain will be less than the no non-interactive type of gain. Fine. So let us take one small example that was question in that was the question in GATE. What is there? This is suppose amplifier A1, this is suppose amplifier A2. So you were given different parameters for these amplifiers. Let us see those parameters. So I'll be writing those parameters here directly, and this was the question in engineering services as well as GATE. Similar type of question, not exactly same. So what is given? I am given for stage 1 AV01 is what? AV01 is 10. Input of stage 1 is 10 kilo ohm. Then output resistance of the stage 1 is 1 kilo ohm. Then overall voltage gain of stage 2 is 5. Input resistance of stage 2 is 5 kilo ohm and output resistance of stage 2 is 200 ohm. And you have to find overall voltage gain and apply this formula. That's it. Or you can, of course, in GATE, if you don't remember, you don't need to mug up it, you just mug it up. The only thing is you should remember the concept. So this is equal to what? That is 10 multiplied by 5. Ri2 is what? 5 divided by 5 and R01 is what? R01 is 1. Ri2 is 5. Ri2 is 5. R01 is 1. So R01 is 1. That's it. And this, the answer of this, this answer of this question is, that is, we have you can calculate this value. Fine. But here I observed one more thing. This was the case when you have open circuit, so that will be your answer. And suppose I have one load connected here. In fact, in GATE there was one resistance connected here. In that case, what will be the output? Output in that case will be V0 will be what? RL divided by, now I have two resistances in series, I have to find voltage across this. So RL divided by RL plus R02 will be the output voltage, simple voltage divider rule. So RL by RL plus R02 multiplied by what? AV02 multiplied by V input 2, and that procedure will be same. The only thing is, I repeat, if you are resistance, that procedure remains same. In previous case, in open circuit case, there is no voltage drop across this, so output voltage is this voltage. But when load resistance is connected, so output voltage will be this resistance divided by sum of 2 divided by this simple voltage divider like this stage. In that case, here it will be RL divided by RL plus R02. That's it. So in that case, if you have load resistance also given to you, so what will be the output? That will be 10 multiplied by 5, AV01 is 10, AV02 is 5, multiplied by Ri2 is what? 5 kilo ohm, right? Divided by Ri2 is what? 5 kilo ohm plus R01 is 1 kilo ohm into 10 to the power 3 divided by RL is what? Suppose RL is given to you and that is 1 kilo ohm. I am taking exact value given to you. RL is 1 kilo ohm. So 1 kilo ohm divided by RL divided by RL plus RL02. So 10 to the power 3 plus R02 is how much? 200. That's it. And that value comes out to be 34.7. 34.7. This is one type of question. So there can be load resistance, there may not be load resistance. So in GATE exam, this was the question which appeared based on the interactive stages, and that was question in electronics 2014 1 mark question. And exactly similar type of question appeared in engineering services also. That was based on the interactive stages. So I hope the concept is clear, funda is clear, and you will be able to handle this type of numerical, whether it is in engineering services, whether it is in civil services mains, or maybe engineering services limbs or mains. So this is all about the voltage gain, current gain, and the power gain of multi-stage amplifier. So I'll be discussing now the different type of couplings in multi-stage amplifier in my next video. So just wait for my next video to come. Thank you very much for watching the video.